Hello, in these problems we are going to deal with some convergence questions with alternating series. Key questions we're going to have here at the given series. Here we've got n equals 0 to infinity, negative 1/2 to the n. We can determine if the series is convergent or divergent. If the series is convergent, we can figure out is the series absolutely convergent or conditionally convergent. So again, the general setup we have is that our series here will either be convergent or divergent. And then if it's convergent here, because it's alternating, what we can do is take the absolute value that'll essentially get rid of some negatives. And if after taking the absolute value, the series is still convergent, then we call this absolutely convergent. If we take the absolute value and the series is now not convergent, so the series was convergent, but you take the absolute value of all the terms and now it's not convergent, we call this conditionally convergent. So the options here that we're asked to find here would be, we're trying to figure out, are we divergent, absolutely convergent, or conditionally convergent? So if you're absolutely convergent or conditionally convergent, that means you're convergent, but it's just a more specific type of convergence. Okay, so our general setup. Now this first one here, I'm going to decide right away, do I think this is convergent or divergent? So right away, this one, I'm going to recognize this as geometric here. So this is geometric with r equal to negative 1/2 here. And so what we get here, geometric series, again, that was n equals 0 to infinity, r to the n. And here we just put a negative 1/2 where the r is. It just is explicitly like a geometric series. And if you remember back to geometric series, this converges for absolute value r less than 1. So now, if you took an absolute value here, so if you took an absolute value of negative 1/2 to the n, what you'd get is 1/2 to the n. Well, that would give you an r is 1/2 instead of negative 1/2. Both of those are going to converge. And so what we get here is essentially we're in the absolutely convergent case. So we have here that n equals 0 to infinity, negative 1/2 to the n. This converges because it's a geometric series with r, absolute value r less than 1. But if you went and did summation n equals 0 to infinity, negative 1/2 absolute value to the n, this also converges. So this is a geometric series with r actually equal to 1/2, positive 1/2. And because this absolute value converges, oh, I guess I should have written it, sorry, negative 1/2 to the n, put the absolute value on the outside. Same, equivalent to what I wrote, but really it should be absolute value of that whole sequence inside here, or each term of the sequence. And because we got our original series converges, and if we take the absolute values of the terms, that new series also converges, that means that our series negative 1/2 to the n, summation n equals 0 to infinity, is absolutely convergent. And that just gives us a stronger sense of convergence. Essentially what that means is that you can add up these terms inside in any order you like. Now that seems like it should be able to happen with any series, but it turns out if you have a conditionally convergent series, you can reorder these in some ways and get, well, actually, if you have a conditionally convergent series, you can reorder the terms and get any sum you like if you just sort of add them, the same terms up in the different order. Let's look at the next one here. So this one, I have summation n equals 0 to infinity, negative 4 to the n over 2n factorial. This one, I see the factorial, and that makes me think here to use the ratio test. So I'm going to use a ratio test. So my thought process here is maybe I have factorials here, and that makes me think use the ratio test. Now, the ratio test is set up really well here for absolute convergence because you can actually take the absolute value of each of the ratio, I guess. So what we're going to do is we're going to take the inside sequence, replacing n with n plus 1. So that's negative 4 to the n plus 1 over 2 times n, which is 2 times n plus 1. I mean to do that factorial. So this is like a n plus 1 over a n. But really, if you look at the ratio test, you can make both of these absolute value. Here. And then the an is, well, negative 4 to the n over 2n factorial. So this works out okay, except we need absolute values. Now, what the absolute values are going to do here is 2 times n plus 1 factorial, that's positive. 2n factorial, that's positive. But the absolute value is going to take negative 4 to the n plus 1, replace that with just 4 to the n plus 1. Negative 4 to the n, replace that with 4 to the n. And what that's going to tell us, essentially, is that if this series is shown to be convergent by the ratio test, it's actually going to be shown to be absolutely convergent. So the ratio test, I guess, probably didn't mention this when we went over it the first time, but not only does it show that series are convergent if that ratio is less than 1, limit of the ratio is less than 1, it shows that the series is actually absolutely convergent. So it's a stronger statement. All right, now let's see if we get the ratio less than, or the limit of the ratio less than 1 or not. So I'm going to take reciprocal of the bottom, gives me a 2n factorial, over, and then after I take the absolute value, the negative 4 to the n becomes 4 to the n. On top, I'm going to get a 4 to the n plus 1, and then I'm going to get a 2n plus 2 factorial. So 2 times n plus 1 is 2n plus 2. All right, now what I'm going to get, let's see, 4 to the n plus 1 over 4 to the n, that's going to give me a 4 on top. I'm going to keep the 2n factorial. Now, this is a little bit tricky at first. 2n plus 2 factorial, that's 2n factorial, times, well, the next term is 2n plus 1, and with factorials you might think you're done there, but we actually need to go up to 2n plus 2. So we get 2n factorial over 2n, 4 times 2n factorial over 2n factorial times 2n plus 1 times 2n plus 2. The 2n factorials cancel, and what we get is that our absolute value of an plus 1 over an is 4 over 2n plus 1 times 2n plus 2. Okay, and then we wanted to take a limit as n goes to infinity here. We were calling that rho. Here is the limit as n goes to infinity, an plus 1 over an. Take the absolute value of that. Note, absolute value on top and bottom, same, equivalent to absolute value over the whole fraction. Well, that's a limit as n goes to infinity. We just calculated what this ratio inside is. It's 4 over 2n plus 1 times 2n plus 2, and that's going to be 4 over infinity. That's going to go to 0. And what happens with the ratio test is rho is less than 1. That means our original series, n equals 0 to infinity, negative 4 to the n over 2n factorial is convergent, but actually we get that this is absolutely, struggling writing this, absolutely convergent. So we get some additional information from the ratio test. Next one. All right, this one again, I'm going to go use a ratio test here. I think it's just kind of the way to make this work out, or looks like it's going to work out. So I'm going to do an absolute value, an plus 1 over an. So an plus 1 is going to be a negative 1 to the n plus 1, that's n plus 2, over n plus 1 times 2 to the n plus 1. So that's all my an plus 1. And then over an, which is negative 1 to the n plus 1 over n times 2 to the n. And I get the absolute value of the whole thing. So what this absolute value is going to do is it's essentially going to get rid of the negative 1 to the n plus 2 and the negative 1 to the n plus 1. So negative 1 to a power is either 1 or negative 1, but once you take the absolute value of that, you're just going to get 1. So essentially negative 1 to the exponents go away. And everything else is positive, so that's all the absolute value is going to do. So I can ignore the negative 1 to the powers. And then after I sort of take the reciprocal of the bottom, I'm going to end up with n times 2 to the n over n plus 1 times 2 to the n plus 1. Okay. Now, this, I can take the 2 to the n over 2 to the n plus 1 and cancel the 2 to the n. So I'll get n over, I'm going to put the 2 in front, times 2n plus 1. So that's 2n plus 1 I can cancel out the 2 to the n. I'm left with just a 2, which I wrote in front because it looks nicer to me. Okay, so now I sort of limit rho, take a limit as n goes to infinity of an plus 1 over an, absolute value. That's a limit as n goes to infinity of, well, we calculated this out here. I guess you could do the calculation inside of the limit as well here. Well, this is going to be essentially n over 2n. That's going to go to 1/2 here. And the key thing is 1/2 is less than 1. That tells me my original series is convergent, was the original way we sort of mentioned or sort of described the ratio test, but it actually tells you the original series is absolutely convergent. So what we get is that the series n equals 1 to infinity, negative 1 to the n plus 1 over n times 2 to the n is absolutely convergent. So it converges, but in a sort of stronger way here. Next one. Okay, now we've got a series. We're going n equals 1 to infinity, negative 1 to the n plus 1 times 2 to the n over n. Now, this one, we could do a ratio test, I suppose, again. There's something I'm going to notice here, is that my terms, actually, let's forget the ratio test. We could do a ratio test. You'd get a ratio that is bigger than 1 here. Actually, I think it'll go to infinity here, and that would show you that this series actually diverges. But for divergent series, what's generally easier to do, often, sometimes this doesn't work, but with the ratio test working out, I think it almost always does, if not always. What we can do is just take a limit as n goes to infinity of, well, let's do, so really the divergence test says take that of am, the thing on the inside. So what we get is a limit as n goes to infinity, negative 1 to the n plus 1 times 2 to the n over n. Now, what is this going to do here? Well, as n gets big, 2 to the n is going to get way, way bigger than n here. So this absolute value of what's inside is going to go to infinity, but as n goes positive, negative, negative 1 to the n plus 1 is going to switch positive, negative, positive, negative. So we're going to get a function that sort of oscillates between positive infinity and negative infinity. Now, I'd say that's really a limit that doesn't exist here. So this does not exist. But all we care about here is that this limit does not go to 0. So we need, for our series to have any hope of convergence at all, we need that this limit should go to 0. So the limit should exist and it should go to 0. Here, like even if you let n be odd here, you'll get, let's see, always positive. 2 to the n over n just is not going to go to 0 because 2 to the n is going to get way bigger than it. And so this just tells us that n equals 1 to infinity, negative 1 to the n plus 1 times 2 to the n over n diverges by, and sometimes you'll hear this called the nth term divergence test, or maybe just the divergence test. So sometimes you say the nth term, sometimes not. But really, this series diverges here. Or you could do a ratio test. You'd get a limit of infinity. Next one. All right, so here we have a summation n equals 2 to infinity, negative 1 to the n, 3 over natural log n. Here. So this one, I look at it and think, well, the ratio test isn't really going to work here. So let's just try our ratio test. I think it's going to give you a little bit of a mess. It's going to give you an plus 1 over an, absolute value. This is going to be 3 over natural log n plus 1 over 3 natural log of n. I don't need my absolute values because as long as n is at least 2, natural log n plus 1 and natural log 2 are positive. Now I got to think about that. Yeah, natural log 1 would be 0. So yeah, these would both be positive here. The 3's will cancel, and you'll end up with natural log n over natural log n plus 1. Okay, so what's our row? Limit as n goes to infinity. It's going to be the natural log n over natural log n plus 1. That gives us an infinity over infinity, so we can use L'Hopital's rule. Limit n goes to infinity. Derivative of natural log n is 1 over n. derivative of 1 over n plus 1, or natural log n plus 1, derivative of natural log n plus 1 is 1 over n plus 1. This is a limit as n goes to infinity of n plus 1 over n. That equals 1. And what we get when we get a limit of 1 here, that tells us that our ratio test is inconclusive. So basically we did all this work and we don't really know if the series converges or diverges or converges conditionally or is absolutely convergent here. I just sort of did not work out here. So this didn't work. Okay, what can we do? Keep the series there. So one thing I'm going to do is we can use, because this is alternating, it's -1 to the n. This is an alternating series. Typically, these are going to converge if this a to the n goes to 0 here. The 3 over natural log n goes to 0, which it does here. So if we have an alternating series, so this is really our alternating series test we're going to use. So our alternating series test what this is going to say typically is that if I take a series about n equals 0 to infinity, but you could start at 1 or 2, -1 to the n, or it could be -1 to the n plus 1, or -1 to the n minus 1, doesn't really matter. an, where I need two things here. I need my an's are greater than or equal to 0. Oh, I'm going to need three things. Where an plus 1 is less than or equal to an. So I need my an's to be decreasing. And what I'm going to say here is that the limit as n goes to infinity of an equals 0. So checking these, I would check the third one first, because if the third one fails, the original series just diverges. Oh, that would happen. Everybody didn't say what these are. So let me say, so we have this. So if we get all three of these, so we have this kind of series, if we get all three of these, that means our series n equals 0 to infinity, -1 to the n, an, converges. So that's really the alternating series test. You just have -1 to the n, alternating positive, negative. These an's have to be positive. If they could be negative, it messes up the positive, negative alternation. These terms have to be decreasing, or at least not increasing, and they have to go to 0. Here. And then we get convergence here. Now this is might be conditionally convergent, might be absolutely convergent. It's not telling us, just convergent here. So what we get here in our case, we have summation n equals 2 to infinity. That's exactly how we wrote this. We have -1 to the n times 3 over natural log n. So here, your an is essentially 3 over natural log n. We're starting at 2 instead of 0, but that won't matter for convergence. The finite number of terms at the sort of head of the series does not matter. And so what we're going to do here, let's check these. 3 over natural log n. As long as n is at least 2, that's going to work out. So an greater than or equal to 0, check. An plus 1 less than or equal to an. So if I increase this an plus 1, if I make the denominator, n plus 1 is bigger than n, so natural log n plus 1 is bigger than natural log n, that means that essentially 3 over natural log n plus 1 should be smaller than 3 over natural log n. And the reason for that is the denominator on the left is bigger than the denominator on the right. So bigger denominator makes smaller fraction. And actually this is a straight up less than. And the limit as n goes to infinity, an equals 0. Well, if n goes to infinity, natural log of n also goes to infinity. 3 over infinity is going to give us 0. So these work out. And that tells us here, what's that tell us is that our series n equals 2 to infinity, -1 to the n, 3 to the natural log n, is convergent here by the alternating series test. Now, that really wasn't what the question asked, though. The question asked, figure out if this series is divergent, which it's not, or absolutely convergent or conditionally convergent. So So now that we know that this is convergent series, we have to figure out, is this absolutely convergent or is this conditionally convergent? I guess I circled this, a little bit premature here. So we want to figure out, is this conditionally convergent or absolutely convergent? So what we're going to do is look at the series where we do -1 to the n, 3 over natural log n, and take the absolute value of that. Now what the absolute value, again, is going to do is just get rid of that -1 to the n. So this is n equals 2 to infinity, 3 over natural log n here. And then we have to ask, is that series convergent or divergent? So this one, what I'm going to do is, in my head, what I'm thinking is that natural log of n is smaller than n here. So this is one of these things we should have a sense of size. If you wanted to show this, really, you could look at, let's see, natural log n is smaller than n, is saying n minus natural log n is greater than 0. Let's call this f of n. And to convince you of that, let's just take a derivative. It would be 1 minus 1 over n. Well, as long as n is bigger than 1, this is going to be positive. It means f of n is increasing. And if you do f of 1, that's 1 minus natural log 1 is 1 minus 0. That's 1 here. And so for 1, this difference is 1. And our derivative is positive. It means the difference is only increasing here. Or really, I'm okay with, eventually you get the sense of natural log n is just smaller than n here. Another method, just for the sake of, to show that, is that if you take a limit as n goes to infinity, natural log n over n, that's infinity over infinity, use L'Hopital's rule, you get natural log n's derivative is 1 over n over 1. This is going to go to 0. And so if the limit as n goes to infinity of the ratio of these two things is 0, that means the bottom one has to get bigger as n goes to infinity. So that means eventually n is going to be bigger than log n here. And in terms of series convergence, that's what we care about. We don't care if natural log n is less than n for n equal to 2, 3, 5. This could be false for the first 100 terms. What we care about is n gets really, really big, what happens. And this limit is saying n gets way bigger than natural log n. So another way to sort of establish this inequality here. Okay, now why did I care about that inequality? Well, if natural log n is less than n, that means 1 over natural log n is bigger than 1 over n here. So if we take a smaller denominator on the left, that gives us a bigger fraction. Back to black here. So I get this. Well, that tells me that this series n equals 2 to infinity, 3 over natural log n, is bigger than the series n equals 2 to infinity, 3 over n. And this series really goes to infinity. What we have here is essentially a harmonic series, except the first couple terms. I mean, it diverges to infinity, or this is a p series with p equal to 1. That's going to diverge. So 1 over n to the 1 here, although the 3 doesn't really matter. I could factor that out. So it's essentially a harmonic series, except I'm not starting at 0, I'm starting at 1, I'm starting at 2. Also, this 3 is here, but neither of those things is going to affect convergence or divergence. So when we get 1 over natural log n is greater than 1 over n, we're going to say 3 over natural log n is bigger than 3 over n. So we add these up. The sum of the 3 over natural log n is going to be bigger than the sum of the 3 over n's. But the sum of the 3 over n's is already going to infinity. That means that this sum of the 3 over natural log n's also has to go to infinity. So what this is, here is essentially, this is a direct comparison test here. I'm sort of writing it out in a little bit different way. But what I get is n equals 2 to the infinity, 3 over log n. This diverges, goes to infinity. And I'm just going to say by, I'm going to leave out the word direct, by the comparison test. Here. Okay, so now what we have is that the original series with the -1 to the n thrown in there, that series is convergent. If we take the absolute values, we get a divergent series. So we have this guy diverges, that is the absolute value. The original series is convergent. So when you have those two things going on, that means our original series, -1 to the n, 3 over natural log n, converges. But if we take the absolute value that diverges, so this is called, this series is conditionally convergent. So sort of a classic conditional convergence result. Next one. So we've got, let me say before that, we've got now problems where we have absolutely convergent series, conditionally convergent series, we have a divergent series. Hopefully you can tell the difference between those. Next one's a bit weirder here. So this one here, here's what I suspect a lot of people would do. Here, is you would say, okay, -1 to the n, hey, that means this is alternating. 2 plus -1 to the n. Let's think about what that is. 2 plus -1 to the n equals, well, let's think here. So if n is odd, I'm going to get 2 minus 1, which is 1, for n odd. So if n is odd, -1 to the n is -1. And then we'll get 2 plus 1, which is 3, for n even. So what we've got here, when you look at this series, is we're really, let's just write out the term, starting at 2, so we're going to get over natural log 2. So 2, we're going to have it positive, and we're going to have 3. So we're going to have 3 over natural log 2, minus, the next one is going to be a 1 over natural log 3, plus 3 over natural log 4, minus 1 over natural log 5, plus 3 over natural log 6, minus 1 over natural log 7, and so on. So when I look at that, it's alternating. And so what I think a lot of people would do is they would say, okay, an is 2 plus -1 to the n over natural log n. And this is an alternating series, so I take a limit as n goes to infinity of 2 plus -1 to the n over natural log n. Well, the top is at most 3. The bottom is going to infinity, so this is going to equal 0. So what we got was an alternating series where the terms go to 0 here. And what that's going to tell me is that the series should converge. So that's what I think, but that's actually wrong. So this was sort of the main condition for convergence. And if we go back up, when we talked about alternating series test, here, we had 3 conditions. We had the an's positive. We got that. We had 1 and 3 over natural log n. That's all positive. We got the third condition, but we missed this decreasing condition here. And that's actually going to fail here because essentially this 3 over natural log 4, the 3's are going to be bigger than the 1's that are immediately next to them. So let's pull up a calculator here, get a sense of that. So let's do, how about 3, actually let's just go to y equals here. Let's do it this way. So the an is 2 plus -1 to the x divided by natural log of x here. And I'm going to go table set. We want to start at 2 and increase by 1. So if we go to the table here, now initially we get is 4, 0.9, 2, 0.6. You can see those aren't decreasing, but I don't really care what's going on now. I really care about really big values. So let's go to table set. Let's not start at 2. Let's start at, well, how about 200? See what happens here. So there, if we're getting natural log 200, you're getting 0.5662, 0.18856, 565, 188. But still, these sequences are going to 0 here. These numbers are going to 0, but they're not going to there sort of going down, 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 down. It goes down, up, down, up, down, up, down, up here. And what happens here is you've really got the sequence of 200 and 202 and 204 and 206, 56622, 56516, 56411, 56308. That part, the even terms are going to 0. The odd terms, the 18856, 18821, 18786, also going to 0. So you've got sort of two sequences. I was going to say sandwiched together, but maybe more interwoven that go to 0 here. And so that's really what's going on. So we lose that sort of decreasing condition of the alternating series test. It means the alternating series test here sort of does not work here. So this would be a standard one where I think people would say that. Now, this example admittedly has been contrived to make this happen here, but hopefully it illustrates the point here. Now the question is, does this series diverge? Does it converge? Now note, these terms, even if you throw in the -1 to the n, the terms inside are going to go to 0. So our nth term divergence test fails. we could try and do a ratio test or a root test. Ratio test is going to give us a ratio of, well, let's try it. The ratio test is going to get us sort of mixed up here, because what we're going to get, that ratio, is either going to be 1/3 or 3, depending on whether it's odd or even. And so the limit is not going to exist here, and it's actually going to alternate between something less than 1 and bigger than 1. Ratio test is going to fail. So what I'm going to do here is use a trick. I'm going to rewrite this. So I'm going to take this written out. I'm going to group these terms 2 by 2. Here. So what I'm going to do is I'm going to take my original series, n equals 2 to infinity, -1 to the n, times 2 plus -1 to the n, over natural log n. And I'm going to try and rewrite this as a summation. How about let's just do k equals, well, 2 to the infinity. So I'm going to write the even term. So it's going to be a 3. So I'm going to take the 2, that's going to be a 3, over natural log. Okay, I'm going to start at 1 with k. Here I want to, and k is 1 for n to be 2. So natural log of 2k. And then minus, so 3 over natural log 2k, minus 1 over natural log 2k plus 1. So I'm going to rewrite this series as an equivalent series that's not going to be alternating. I'm going to sort of build the subtraction in. That'll make all of the terms positive. So 3 over natural log 2k minus 1 over natural log 2k plus 1. And so let me just check this. When k is 1, I get 3 over natural log 2 minus 1 over natural log 3. That's this grouping in red. When k is 2, I get 3 over natural log 4 minus 1 over natural log 5. That's this grouping in red. When k is 3, I get 3 over natural log 6 minus 1 over natural log 7. That's this grouping in red. So we get the same series here. And now this, when I look at this, I see 3 over a natural log here. Well, natural log 2k, I'm not going to worry about that too much. I'm seeing essentially 3 over a natural log here, and that's going to be divergent. We did that on the previous question. We don't have the -1 to the n. If we had the -1 to the n, it's an alternating series. It's going to give me conditional convergence. But without the -1 to the n, if I just had the 3 over natural log 2k, not the -1 over natural log 2k plus 1, that would be divergent. So I'm taking an infinite series, but then I'm subtracting another infinite series, and how do these balance? So I'm thinking this is going to diverge here, and to show that, I'm going to do 3 over natural log 2k minus 1 over natural log 2k plus 1, and I want to get something that's smaller than this. So how do I make this smaller? Let's see. Well, I could subtract something bigger, or add something smaller here. So let's see. I kind of want these denominators to be the same. So if I removed this, let's just try this. I don't know if this is going to work out. So what I'd like to do is change my 2k plus 1 on the second term just to a 2k. If I do that, 2k plus 1 got smaller. That makes the denominator of smaller, which makes this fraction bigger, but I'm subtracting that, so that makes the whole thing smaller. So this inequality is actually true. So if I replace the 2k plus 1 again, it makes 1 over natural log 2k plus 1 smaller, which makes, no, sorry. If I replace 2k plus 1 with 2k, it makes my natural log 2k plus 1 smaller. Denominator smaller, makes the whole fraction bigger when I go from left to right, but I'm subtracting it, so that makes the whole sort of quantity expression smaller. And this is 2 over natural log 2k. So what I get here is really this series is bigger than summation k equals 1 to infinity, 2 over natural log 2k here. And then we could do a comparison test here. Let's do a limit comparison just to show that. So I can do a limit comparison. Here I'm going to do a limit as now k goes to infinity, normally n, but we've got k's here. And I want to show this diverges. So sometimes what I'll do is just compare it with 1 over k, or 1 over n, typically. And the idea here is that, well, let's see what happens here. So limit k goes to infinity. I'm going to get 2k over natural log 2k. That's infinity over infinity. I can apply L'Hopital's rule here. Gives me 2 over, let's see, over 2k, 2 over 2k. Note the 2's cancel. This is really natural log 2 plus natural log k. So its derivative is really just the derivative of natural log k, which is 1 over k. In any case, I get a limit as, whoops, not n, but k goes to infinity of 2k. This k in the bottom comes up, and that's going to go to infinity. Now, what we got then, and this goes to infinity, means our top is bigger here. So that essentially says that 2 over natural log 2 over natural log 2k is bigger than 1 over k. And that means in terms of our series, this series that we're dealing with, the k equals 1 to infinity, 2 over natural log 2k, is bigger than k equals 1 to infinity, 1 over k. And I have a little bit of an issue here now that I look at it. When I plug in 1 in this series here, I get natural log of, no, 2, that's fine. I was worried about getting a natural log of 1, but it's 2. So yeah, I can actually leave the k equals 1 there. I was worried I have to jump that to 2, which would be just fine. And we know this series is divergent, and it's divergent in the way that it goes to infinity here. So that tells us that our original series is bigger than some version of infinity, so our original series is divergent. So what that gets here is that the sum n equals 2 to infinity, negative 1 to the n, 2 plus negative 1 to the n over natural log n, in parentheses here originally, this is actually divergent. And I'll put some exclamation points there because, I mean, I get again this result where the terms inside go to 0 and it's alternating here, but the series is not convergent here. And that's because the going to 0 is sort of two interwoven sequences where the positive terms were bigger than the negative terms, and so you can kind of play them off each other. Okay, I just want to point out one more little thing here. This limit, I did L'Hopital's rule. But again, if you start getting familiar with the sizes of various functions, here you have 2k versus natural log 2k. This is like n versus natural log n. And you can see right away that k is bigger than natural log, or sorry, n is bigger than natural log n. And so you could have seen right away this limit goes to infinity. So you can eventually build intuition here. It might speed you up. Not that L'Hopital's rule was that hard here. Next one, we're going to do something different. Related, but different. So here we want to estimate each series here with an error of less than 0.001. So we want to get a value of the series within 0.001. The way that's phrased tells you all of these series should be convergent here. So we're going to get a bunch of alternating series here. And there's sort of an, I don't know, probably an alternating series. Maybe we'd call this estimation theorem here. And essentially what this says is that if I do a summation n equals 0, let's say, doesn't really matter where I start. How about to the let's just do a capital K here, and I do a negative 1 to the n times a sub n. So I'm going to do this. Well, let's say I don't really want a k. I want to do an infinity here. And what I'm going to do here is that if I subtract n equals 0 to the capital K, negative 1 to the n, a sub n, that this difference. So here, what we're doing here is we really have a series which is an infinite number of terms. Typically, that's what we care about. But we can't add up an infinite number of things. So we add up some finite number of things. So we go to k here. And the difference between these, that's how far off we were. So the alternating series estimation theorem says essentially if this series satisfies the conditions of the alternating series test, we can bound this above by a really simple bound. It's the first term that we're missing. And what we need here is if 1, I need that my an's are all greater than or equal to 0. 2, I need an plus 1 is less than or equal to a1n. And I need the limit as n goes to infinity of the an's equals 0. So these are just our conditions for the alternating series test. If you have those, you can estimate an alternating series really easily. So here, what we're going to do is we need to get an error of less than 0.001. Here, so that's 1/1000th. So we need the first term we look at. So let's do summation n equals 1 to infinity. negative 1 to the n plus 1 over n. So that's alternating. If we're starting at 1 versus 0, doesn't really matter. And then we're going to approximate this by adding up, sorry, not starting at 0, we're starting at 1, up to k, negative 1 to the n plus 1 over n. So we're going to add up the first 10 terms, 20 terms, so on. And we're saying this is bounded above by the first term, really the a part, the absolute value of the first term we're missing. So be it positive or negative, we take the absolute value. And that's 1 over n plus 1. So this is what our alternating series estimation theorem is saying for this particular series here. Well, what's that? 1 over n plus 1 here. We want that to be less than 0.001. That's 1/1000th. So we want this error to be less than 1 over 1,000, really less than equal to, and you can achieve this by letting, not n plus 1, k plus 1. First term we're missing, we take the k plus 1. And the way to achieve that is you could let k be 999, or k equal 1,000, or something bigger than 999. So what we're going to do here is, that just gives me, how many terms I need. I need k equals 999 terms to get my error less than 0.001. And so my estimation is going to be summation n equals 1 to 999 negative 1 to the n plus 1 over n. So I'm going to try and use my calculator. I'm a little worried this might not work here. The way to do this is I go second list, I go to math, I do a sum of second list ops sequence here. And I'm just going to put in the, negative 1 to the, I'm going to use an x divided by x in place of n. And I do x from 1 up to 999. I think sometimes this sequence is too big. Here, I forget exactly what happens. Let's see if it works. Sometimes it'll give me some kind of overflow error. Oh, no, it did work. Okay, so we want this error less than 0.001, so that tells us 0.693, so it actually is negative 0.693. And then we get a 6 here. So let's see, if we did 0.693, that would give us, up to 694, 692. So this would actually be a value that's within 0.001, because we know our value, oh no, it's not necessarily, because we could go 0.01, could be 6, so wait, we got to think about this here. We want an error of less than 0.001 here. So this tells us our error is at most 0.001. Maybe we want to do 1,000 terms here. Well, I'm not so concerned about this. So essentially I'm worried about, essentially if I do all these decimal places, maybe that error is exactly 0.001 from here, and the actual answer is 0.694647430, and the 6 was rounded. Maybe that gives me some kind of error. But I'm just going to do negative 0.693. Whoops, 6, 4, 7, maybe. Put a bunch of decimal places. And essentially that'll get us there. You can go to 1,000, you get an error of 1/1001st here, 1 over 1,001, and then you could bound that error even with the rounding. Okay, so that's really our estimate for this series here. Now a question you might ask is, well, what if, let's insert, how about we go up to 1999? Let's go up to about 2,000. See if we get anything different here. Now we're going to have to wait a while here. So we're saying that should be our error. How close was this? Oh, and now that was too big. So let's try something else. Maybe 1,000 is the limit. Hit enter. Let's try 1,000. That'd be a somewhat logical, well, typical limit of these. Yeah, so 1,000 is too big. You can only do 999. What you could do is add up this to 999, and then add up from 1,000 to 1,500. So you could do and say, well, I've already got the thing to 999. Then we do 1, 2, 3, 1,000 up to 1,500, say. We'd add on another 500 terms. So we could take our original decimal, this, and add whatever this is. And the idea here is this should be less than 0.001, less than 1,000th, which it is. question here. What's the real answer? Well, we'll learn something later on here that essentially what we're going to get, let's see, this one is going to be, is this right? Yeah, it's going to be, well, essentially, if I do natural log of 2, oh, I messed this up. That's why. This is n plus 1. I don't have the plus 1 there. So what I did, actually I have a wrong answer here. I didn't put in this plus 1. Well, what's that do? It makes every term negative. So all that's going to do is change this to positive. So let's just go back and do that anyway. So let's go pull up some of these. So let's go here just to convince you of this if you don't believe that. So delete. Sorry, this got a little bit off. Insert a plus 1. And now we calculate this, and it should give me the positive version here. Exactly what we had before, but we have to wait a while. Notice this takes some time here. So what we're going to see later on, though, is that this original series has something to do with some other series. So this is going to be a type of power series. And this value, 0.6936, here and so on, really what we're calculating is actually natural log of 2. So there's natural log of 2, 0.6936. Notice the error ends up in the 4th decimal place, and we said we want to have this accurate through essentially 3 decimal places, which is what we got here. So it's really what's going on here, and we'll see why that's natural log 2 later. Really, it's not something you should be able to see at this point. I use a power series, or maybe a Taylor series. Next one. Same thing. This is the same series now with, instead of the n plus 1 is the n. Well, that's what we just did. It's going to turn all the terms negative. Here, we already did that here. So this is just going to be the negative 0.69. I forget what it was. 3647. So everything's exactly the same as before here, except sort of we get the negative here. All the terms change value. And then we get, really, this is negative natural log of 2, which is actually natural log of 1/2 here. And you get the negative on the value. Okay, so essentially the same question. More interesting here. Negative 3 to the n over n factorial. Starting at n equals 0. So again, what we're trying to do is we want a summation n equals 0 to infinity. Negative 3 to the n. Whoops, let me write that a little bit more nicely. Negative 3 to the n over n factorial. And this, first of all, we want to write this as an alternating series. That negative 3 to the n I can write as negative 1 to the n times 3 to the n over n factorial. And what I want to do then is approximate this infinite series with, do n equals 0 up to some k. Negative 1 to the n times 3 to the n over n factorial. And this is this 3 to the n over n factorial will satisfy our conditions for the alternating series test. You could check that. It'll go to 0. N factorial is bigger than 3 to the n. So if you did like n is 100, you have 3 multiplied by itself 100 times. You have 100 factors on the bottom here, but they get a lot bigger than 3. They get up to 100. So 100 times 99 times 98. 1 and a 2 are smaller, but you can pick those off with like a 27 will kill the first couple 3s. And what our alternating series test says here is that this error is at most the first term we leave off. That's k plus 1. That's 3 to the k plus 1 over k plus 1 factorial. And we want that to be less than 0.001. Okay, so before what we had is we had like an n down here, 1 over n. We just solved explicitly 1 over k, or maybe a 1 over k plus 1. We solved explicitly what k would make the thing on the error bound equal to 0.001. We're not going to be able to do that here. So what I'm going to do instead is just use my calculator here. I'm going to plug in 3 to the x plus 1 divided by x plus 1 factorial. Now, to get factorial, I go to math. And this PRB is probability, and then it's option 4, or whatever option is on your calculator. And I'm going to go to set my table. I think I'm starting at 200. Let's start at 0. And I'm looking for the first one that's less than 0.001. So you notice here 3, 4.5, 4.5. These are fairly big for a bit. Eventually they get small. They should get small relatively quickly. There we go, 12. So what we want here is that if we plug in 12, let's make sure I type that in right. X plus 1, x plus 1. It's worried I did it x instead of an x plus 1 somewhere. So I need really x here. So what I'm going to do here is k, this is true, for k equals 12. And I just used my calculator to run through some values here to check that. I didn't really have to solve for anything. The factorials and exponents, that's going to be really hard to do here. So what I get is that my summation n equals 0 to infinity, negative 3 to the n over n factorial should be about the same thing as n equals 0 to 12. Negative 3 to the n over n factorial. And that I can calculate. So what we're going to do is, again, second list math sum, second list ops sequence. We're going to do negative 3 to the x divided by x, and then do math prob factorial, comma, x is our sort of index that we're using, and we're going from 0 to 12. Here, close the sequence, close the sum. And this is going to spit out some value. We expect this to be 0.049997, all right. Looks like 0.05 here, maybe. That's not it. This is really our answer for this problem here. What is this? So if we do a power series later on, my claim here is that this should be like 1 over e cubed. So there's something with some power series. We'll see how to connect this particular original series with 1 over e cubed later on. So I'm going to do 1 divided by e to the third. And you'll see it's 0.049. I got my first 3 digits right, and then there's a little bit of error in the 4th digit there. So if you added up more and more terms, you'd get closer to this. If you're not convinced of that, let's go not to 12. Let's add up, I don't know, 100 here. Do that. It'll take a while to think. Oh, overflow. The factorial got too big. Not sure how big I can go with factorials. Let's try 20. Let's be less ambitious here. And 20 already, we got 870,685 versus 684. My guess is if you went to 30, there I got the 4 to match up here. So we got, however many digits there are. There's going to be some error still in the end, but it's getting really, really small here. So this series, you can estimate with relatively small number of terms. The previous one, we needed like 1,000. Essentially here, we needed, what, 12 or 13 terms, I guess. Last one. Here, same deal as before. This is going to be an alternating series. It's going to converge by the alternating series test. We can use the alternating series estimation theorem here. What we're going to get here is that this series minus summation n equals 0 to k, negative 1 to the n over, what do we have, a 2n plus 1 times 2 to the 2n plus 1 here. So if we do that, that error is going to be at most the first term we're missing. That's when we get a k plus 1. So we're going to get a 1, absolute value, makes the negative 1 to the n go away. We're going to get a 2 times k plus 1 plus 1. That's our 2n plus 1 with k plus 1 plugged in for n, times 2 to the 2 times k plus 1 plus 1. So note that what we get here is that error is 1 over 2k plus 2 plus 1. That's 2k plus 3 times 2 to the 2k plus 3. And we'd like that error. For this problem, it was stated, hey, let's try it less than 0.001. Could be whatever we want here. And I'm going to use the same technique as before, as the previous problem with the factorials. I'm not going to try and solve this sort of algebraically or by some other means. I'm just going to brute force this with a calculator. Let me clear this. I'm going to do 2x plus 3 times 2 to the 2x plus 3 here. And then build a table of values. Note, oh no, that's not what I want at all. Here, these are getting really big. What I forgot is 1 divided by. 1 divided by, parenthesis, and then close parenthesis. Table. And then already, you'll notice, 0.001, we just need 3 here. So that's pretty slick here. This is really, really quick here. What we get here, let's see, if we do 3, so what we get for this is we need k equals 3. So that tells us here that our original series, summation n equals 0 to infinity, negative 1 to the n, 2n plus 1 over 2 to the 2n plus 1. This should be about, just add up n equals 0 to 3. That's 4 terms, negative 1 to the n over 2n plus 1 times 2 to the 2n plus 1. Now I could use the sum sequence set up in the calculator, or some of the more updated calculators have actually like a summation notation you could do here. This one, there's 4 terms, I could write this out. When n equals 0, I get a negative 1 to the n is 1, starting positive. So 1 over 2n plus 1 is 1, 2 to the 1. So I'll get a 1/2. Next one, I'll get a negative 1 to the 1. That's negative. Let's see, when I plug in 1, I'm going to get a 3 times 2 to the 3rd. That's 8. Let me write it out as 2 to the 3rd. 3 times 2 to the 3rd. And then I'll get a plus 1 over. So this is, first one is 1 times 2 to the 1. Next one is 5 times 2 to the 5th. And then minus 1 over 7 times, whoops, not 7, but 2 to the 7th. So what that is, this is a half, minus 2 to the 3rd is 8th, times 3 is 24. 2 to the 5th is 32, times 5 is 160. Minus 2 to the 7th is, what, 128, times 7. I don't know what that is there. Trying to figure it out. It's probably like 896 is my guess. 840, yeah, so this is 896, 1 over 896 here. So you can approximate this that way. So what I'm saying here is that this series should be 1/2 minus 1 divided by 24 plus 1 divided by 160 minus 1 divided by, I'm just going to do this, 7 times 128. Plug that in, and I get this to be about 0.463. So that's what we have here. Okay, 463, and maybe I should do another digit here. Maybe 463, 463, and then that 4 would round to a 5. So something like that. Here, I'm going to do more digits. Now, what's this? This turns out, it should be really an inverse tangent. So this is tangent inverse, or arctangent, of 1/2 here. So that's the claim here. It should be about 0.4635. Something about a power series tells me that. That's my memory. I'm less confident about this. Not the power series I'm as familiar with, but turns out, yeah, that's the one it is. So 0.463. Oh, I messed it up. 46346, 46364. So I have an error of like, well, it's in the 4th decimal place. That's really where error can be, whatever it wants to. Okay, so that ends sort of our sheet of problems dealing with the alternating series test and the alternating series estimation theorem.